My name is Martin Büchner. I will present our recent work on language-grounded dynamic scene graphs for mobile manipulation, short MoMA LLM. This is joint work between the University of Freiburg in Germany and Toyota Motor Europe. So in our work, we tackle the problem of interactive object search, which requires finding objects in previously unexplored environments that contain closed doors and target objects that are being hidden in articulated objects such as drawers, cabinets, or fridge or something. So basically, the embodied agents basically have to shape the scene in order to solve the task at hand. LLMs have shown remarkable capability in terms of high-level reasoning, and this was mostly demonstrated in tabletop scenarios or fully observable environments in navigation scenarios. In mobile manipulation, however, we face a different set of challenges. So basically, we first of all have large-scale scenes which require an efficient representation for spatial and temporal reasoning. And secondly, we face unexplored and dynamic environments. And third, we also have a high-dimensional observation and action space that scales with the number of objects in the scene. So to tackle this, we present MoMA LLM that is able to take instructions in the form of natural language, ground those in dynamic scene graphs over, that cover basically multiple regions in an open set manner. And lastly, we provide high-level reasoning for mobile manipulation. So first of all, we have our embodied agent that is placed in the scene and that is previously unexplored, and we assume access to RGBD observations and semantics. Given these observations, we dynamically construct a 3D dynamic scene graph, including a navigational Voronoi graph that covers the distinct regions of the environment, and we also do semantic classification of the rooms in the environment. And basically, we provide a structured knowledge representation of the scene graph to a high-level policy that we use for reasoning, basically for mobile manipulation. So how does the policy look like? We have a general task specification, for example, something like find a stove in the apartment, and then we interleave this with a set of high-level actions that is available to the agent, which includes navigating an object, closing of an object, or exploring unseen regions, as well as calling done whenever the task is deemed to be completed, basically. So secondly, we list the set of regions and the contained objects taken from the scene graph in a natural way. And we also define certain unexplored areas within the scene, within each region, basically. And we also add the previous 5 executed actions in order to do long horizon reasoning by considering the last executed actions, including success or failure of these actions. And finally, we ask the LLM to select a high-level action to execute, including the entities in the scene, meaning, for example, the room and the object that you want to manipulate. Throughout our experiments, we basically found that this more natural way of providing information to an LLM policy increases success rates compared to JSON formatted data that was used in previous works, just as a detail. So how do our downstream policies look like? We have an A-star planner that we use for general navigation. So we have a mobile manipulation policy where we make use of previous work called N2M2, where we have a joint navigation and mobile manipulation policy that is trained through reinforcement learning that transfers zero-shot to real-world environments. And lastly, we do classical frontier-based exploration to explore novel areas. So we basically simulate this in iGibson, and we find that that MoMA LLM outperforms previous zero-shot methods as well as trained methods, generally given reasonable time budgets, as you can see on the horizontal axis. And as part of our work, we also introduce a novel metric called org-E, which is basically the area under the curve of the efficiency. So at the area under the efficiency curve, which alleviates the need for setting a maximum time budget that you consider for success. So all in all, we obtain the high success rate, SPL, as well as org-E. compared to previous methods, while minimizing the number of object interactions and the distance traveled. We also demonstrate these capabilities in real-world environments using a Toyota HSR mobile manipulator, where we have a scene with multiple rooms and with closed doors, closed drawers, cabinets, and so on. And we find that our MoMA LLM policy decreases the number of object interactions while covering less distance. So this is how it looks. In the real world, we also show that our policy also transfers to more complex tasks, such as I am hungry, find me something for breakfast. So here you can see our robot is being situated in the living room of this apartment. And we first turn around to explore the first room and the high-level policy reasons to open up the door that leads you towards the kitchen area of the environment. So we open the door, we explore multiple areas. So on the kitchen counter, you may already see there's coffee and there's cereals. So the policy incorporates that in the next high-level reasoning step. And we decide, okay, maybe the closed fridge may open up new areas to see other objects relevant to the task instruction. We use these end-to-end policies to open the fridge, and we see milk. And finally, our MoMA LLM policy reasons about its actions, and we say, okay, cereals, coffee, and milk make up a complete breakfast, and our agent calls done. So thank you very much for your attention. The task definition and the code is available on GitHub, so please feel free to check it out. Thank you very much.